Hi, this is part 2 of the lecture Homogeneous Systems of Equations. So we're working with linear systems that have the vector of constants. Remember the notation ALS for linear systems, and in parentheses we have two arguments, the first of which is the matrix of coefficients. I'm using a letter M here for matrix of coefficients, and B is the vector of constants. More precisely, what we're calling homogeneous system, right, is a system that has some matrix, and this vector of constants is a vector of zeros. Okay, so we're always using the little n notation to denote the number of variables, and the little m denotes the number of equations. Okay, so this type of representation, this theorem is mentioning that if we have a system for which the matrix of coefficients has capital M here, has m rows, and then it has n columns, then this number of columns is a lot larger than the number of rows. Okay, so this system, this would be the vector containing all the solutions, the variables, and this system would be equal to the vector of constants, right? Which in this case, this vector of constants is a vector made of zeros. So there's a bunch of zeros here. It's a column vector made of zeros. Okay, so this is the representation. This system is saying, look, when you have a matrix of coefficients that has much more columns than rows, then this system has infinitely many solutions. Okay, so infinitely many solutions, this we should keep in mind that this means this is a homogeneous system, infinitely many solutions. This means that scenario in which we have dependent variables, okay, dependent variables, and we also have free variables. Okay, this is a scenario in which we write the solution set vector form, and we substitute the entries of dependent variables with expressions that are given in terms of the free variables. Okay, so that sophisticated way of representing the solution sets is something that is guaranteed to happen when we have infinitely many solutions, something that this theorem tells us happens whenever the coefficient matrix has many more columns than rows. And so here we have a definition. This will be a set. This set is denoted with this notation. This is an n for null. Right? It's a fancy n. This is referring to a matrix. So the null space of a matrix, n of A, is the set of all vectors that are solutions to the homogeneous system. The homogeneous system that has that matrix as the matrix of coefficients. Okay, so what this is telling us is that the null space of the matrix is equal to a solution set. And is the solution set of this system, the system that has that matrix with the vector of constants being the zero vector. That is what will be referred to as the null space of a matrix. So let's consider this system with 4 equations and 7 variables. So we consider this system with 4 equations, 7 variables. The augmented matrix is a matrix that is it has 4 rows and 8 columns. Okay, and this matrix row reduces. So the augmented matrix row reduces to this matrix here, and from this calculation, From this calculation, let's see what we can say. That 1, 2, 3, so the number of non-zero rows in the RAF is 3. We had previously noted that the number of variables is 7. So n minus r will be different from 0 before. And this right away is an application of that theorem. This is an example in which the coefficient matrix has certainly more columns than rows. The number of columns exceeds the number of rows. You can see the shape of this rectangle is similar to the shape I had sketched there before. This is also pointing, so we can make a couple of notes here, that the set with the indices of pivot columns, this set contains 1, and then we have 3, and then we have 4. Okay, and the other set F is going to contain 2 and 5, 6, right? 2, 3, 4, 5, 6, 7, and 8. 7 and 8. Okay, so the dependent variables are going to be x1. This here implies that x1, x3, and x4 are the variables that we're going to classify as dependent. Okay, so by reading the information from row 1, 2, and 3, right? By reading the information from each row, realizing this is the RDF of the augmented matrix, so we kind of need to think of the last column there, right? So as the last column is the vector of zeros, so we would write x1, 1x1 plus 4x2, so on. Right, so it's calculation. Let me do the calculation here. You should do row 2 and 3, but I'll write this here. 1x1 plus 4x2 plus 0 x3 plus 0 x4 plus 2 x5 plus 1 x6 minus 3 x7 equal 0. And since x1 is a dependent variable, then we can solve for x1. You can say x1 equals, and then solve for x1. That's something I'm going to indicate here. Leave you pause the video here and do this calculation. Complete solving for x1 from the first row. From the second row, solve for x2, and from the next row, from the second row, solve for x3, and from the next row, solve for x4. You will find expressions, and those expressions are precisely the expressions that will be substituted on entries x1, x3, and x4. Okay, so when we write the solution set in this form, then those expressions will be indicated. Here the free variables are x2, x5, x6, and x7. But more precisely, the one thing we should point is that the matrix of coefficients in this problem, this matrix of coefficients, this matrix over here, that matrix is going to have a null space. Okay, that matrix, if I say that is the matrix A, then this solution set is the solution set of that system, but this also is the null space of that matrix A. Okay, and so in this example, given that the solution set of that homogeneous system or the null space of that matrix of coefficients contains infinitely many solutions, you could compute specific solutions by setting certain values, setting the free variables to certain values. Okay, for example, look at these are examples of by setting the variables to specific values. Here, the second variable is 0, right? So this vector has 7 entries, and this means that x2 here was set equal to 0, and then we have x3, x4, and this would be x5 being set to 0, and x6 being set to 0, and x7 being set to 1. So if the free variables, I'm sorry, this x7 being set to 1. So if the free variables are set to specific values, then we can substitute, plug in these values into the expressions for for the dependent variables. So it's straightforward to verify that in that first example, x2, x5, x6, they're all set equal to 0. Okay, and if the only thing that is non-zero is x7, so by evaluating those entries, if each of these expressions is set to 0, the first entry here, the only thing that's left is 3 times 1, which is 3. Right, so we have something like 0 minus 4. If x2 is 0, then that is 0. If x5 is 0, 2 times 0 is 0. If x6 is 0, then this would be minus 0. So you have 0 minus 0 minus 0 minus 0. So 0 plus 3. The second one set to be 0. x5, x6 are 0. So here you have minus 5 times 1. That gives you minus 5. x5, x6 are 0, so that gives you minus 6, and then you have 0, 0, and then 1. Right? So this evaluation is precisely what leads to having this specific. And why are these values set to that? Is because, as for the sake of illustration, they are free variables. You can choose to set them some values, specific values, and then that would lead to have a specific member of that set, which would be considered a solution. Okay, and so similarly, by setting the free variables here all to be 1, then that would lead to have this other specific solution. Okay, so this is just to score the point that indeed a set of this type contains infinite many solutions. For each value of a free variable, you have one specific solution, and there are infinite many choices since the free variables are allowed to take any value on the complex plane. And the way to verify these are solutions is to plug in these values into the original equations. And what is being pointed out here is that if you were going to use this vector and plug in these values substitute the values of x, each value of x with each of these values, then you would find that that doesn't satisfy the equations, doesn't satisfy the equations of the homogeneous system, and therefore is not a member. This vector, in this case this vector z, is not a member of the null space of the matrix of coefficients of that homogeneous system.